Okay, all right, I won't repeat everything I said, but to recap, what we're trying to do over here is that we're gonna try to look at how to update the beta prior from the beta prior from its prior to this posterior. At the end of the day, as we know, we're working with a continuous prior. So we're gonna work with a continuous version of the Bayes rule in our update. And through that, we get to work with the beta distribution a little bit more. So what I want to also just remind us, the step 2 of our 3-step Bayesian inference updates is that we're gonna work with the data and likelihood function. And recall, we always write the likelihood as a capital L. And don't forget, the likelihood function, it is a function about the unknown parameter. So we usually use this kind of notation when we're working with parameter P in this case. Okay, so recall that we are having a survey sent out to n equals to 20 customers. And we got 12 responses or 12 guesses. And we know that, once again, likelihood is a function of the quantity of interest. So recall this is the binomial PMF. And the quick exercise for you all is to write out the likelihood function one more time quickly for n equals to 20 and y equals to 12 when we are using this kind of notation. Okay, so just 1 minute pretty quickly. And for anyone in the chat, I will put you in one breakout room, I guess, and then I will bring you back as well. All right, so we did this exercise before, so it should be overall straightforward. But at the end of the day, we try to write it in terms of a function of P, because once we know what Y is, the data is given, right? So Y is given, N is given. So it's going to be a function about P, which if we write it out, going to be LP, which is 20 choose 12. So that's the N choose Y part, and then P to the power of 12, and then 1 minus P to the power of 8. Okay, so it should be exactly the same as before. So the story here is that no matter what kind of prior you use, if we were using the same data model and it's the same data set in this case, as well as we're working with the same parameter, which is P, then the data or the likelihood part wouldn't change. So you will see that it's the same as before, but the main new thing that we're going to talk about today will be how to work with the continuous prior. So the Bayes rule for continuous priors, just also recall what we did with the discrete case, is that we're working with a particular posterior probability, for example, PI. And in our illustration, I think we chose 6 different values for PI, right? And then we're able to do that calculation. So the Bayes rule overall is at the top, we have the joint of PI and Y. And in the bottom, due to this probability result, we know that this will just be the general marginal distribution of the data itself once we work out the process. So of course, the posterior case or the Bayes rule version of this for continuous prior will be something similar. And we know that instead of doing a summation, we're going to do integration, because P right now is continuous and we don't have a discrete number of cases to go through. So for us, the focus is how to turn this into a integration when PI can be anything between 0 and 1, and that is based on our beta prior before. All right, so with that in mind, I want to show you the general process. Okay, so we know that we're going to change this into an integration from summation to integration because we're doing a continuous case. And one thing I want to also mention is that the denominator, as we know, eventually going to become Fy after we do in the integration, because we know over here, pi p times LP. So pi p times LP, as we know, is equivalent to pi p times y given p. So that's just a different way, right? Writing out the likelihood. And then because this becomes the joint, and if I integrate out p, I will get the marginal of y. So that's what this denominator is about, which is also coming from our previous review. So one thing very useful in any kind of Bayesian inference, especially with continuous prior that we're working with right now, is because, well, if I know the denominator eventually going to just become the margin of y, and remember in Bayesian inference, we assume that the data is fixed. Okay? So because of that, I can almost not to bother working with this Fy altogether. So you will see quite often today, as well as in the future, that when we're working with continuous case, okay, we're actually just going to focus on the numerator itself. The reason is because the denominator becomes a constant or fixed once we integrate out that. So a lot of times, instead of writing out the full equation with the integration in the bottom, we are able to put that into the proportional sign because we can consider that as a constant. So we're going to work with this version of the Bayes rule first, so we can derive what we call the beta posterior. But then I will also present a version that we do not throw out the constant, but then keep it over there and try to see if we can arrive at the same result. So the takeaway message here is that a lot of times we're going to work with the proportional case. And that, as you can see, we take out of the integration. Usually the integration is the most challenging stuff to work with. So if we can throw that away, everything becomes much easier. So we're going to do that version, which is what we usually going to do in the future as well. But then we're going to come back to the case where we do not take that as proportional and we keep all of the constant in, and we can verify that we will be able to arrive at the same posterior. Okay, so with that, I want to show you how to do our step 3 for this case when we have the posterior, or I should say the prior is a beta, which is continuous. So here we have this proportional sign, okay, and we are multiplying the prior and the likelihood. And we actually have the prior, which from before we have this particular beta. And then the likelihood we know is from a binomial, and we need to derive this p given y. So I have over here the general expression for the prior and for the likelihood. And I will ask you to practice or try out a little bit of how to figure out the product of the pi p as well as the LP over here. So take the product of these two and try to combine the terms a little bit to see if you can recognize anything about the posterior. So we know that Bayes' rule gives us this result. To get the posterior, you need to multiply the prior and the likelihood. So I give you the prior right now in this particular beta format. I give you the likelihood in this binomial format. And there are certain things we can do working with those forms. And so give it a try. This is mostly like an algebra exercise. And then we're going to look at how to recognize the posterior to be another beta distribution. And then we're going to go from there. So with that, all right. So it looks like many of you are trying to combine the terms, right? There's one thing very special about this case, and which when we first introduced the beta prior, I mentioned it a little bit, because you remember when if P follows beta AB, we know that the density of P, right, is going to be 1 over the beta function AB. Don't worry about that for now. And then P to the power of A minus 1, and then 1 minus P to the power of B minus 1, right? So when I introduced that in the first place, I was saying that, well, at least this part of it looks very similar to a binomial density, okay? So what we're going to do here, especially we expressed it out with specific A and B values, okay? And for our likelihood, we have n equals to 20 and y equals to 12. So with that, once we take the product, it's pretty natural, try to combine the powers of P and the powers of 1 minus P from the two terms. Okay, so let's do that. And I'm sure many of you have done that part already. And I'm still keeping the constant over here for now. Okay, we're gonna see how we can work with that later. So what I mean by that, so remember, this is the first straight line that we know, because this is based on the proportional version of our continuous Bayes rule. And then I keep all of the constant 1 over the beta function AB, and then the choose function over here as well. But remember, those values you can calculate, they're fixed, okay? They're a constant. So the natural next step is, well, we have those P terms. So this is a function about P. So we're still going to keep everything about P going on. But 1 over the B, as well as 20 choose 12, they're constants, so they can also go into the proportional sign. Okay, so that will be what we do next. Okay, so this is what I mean by drop the constants, because they're constant in terms of P. We don't need to worry about it. So they go into the proportional sign, and all we have is to combine the powers. So we're going to get P to the power of 15.06 minus 1, and then 1 minus P to the power of 10.56 minus 1. So everybody kind of agrees at this point, okay? So combining the powers gives out those two values, okay? Now what's new here, I guess, is recognizing this 1 over b, the beta function, as well as the choose function, both of them are constants in terms of p. So they can go into the proportional sign as well. So at the end of the day, this should be, if we put everything into the proportional sign as constants, this is what we're going to have. Okay. So one very interesting result about this beta is, so once again, I wrote it on the previous slide. If we have beta AB as the parameters, then we know that the density of P is 1 over the beta function AB times P to the power of A minus 1, and then 1 minus P to the power of B minus 1. And earlier, you're probably wondering why I never really subtract 1 and then just do like 14.06 and then 9.56 over here. Is because if we arrive at this point, we know that this is the posterior distribution. Right? By definition, it's the product of the prior and the likelihood. And I arrive at this point. So very interestingly, we can actually recognize if I think this is my new A, and if I think this is my new B, I'm going to have a beta posterior to be 15.06 and 10.56. And I can write this as P given Y as the posterior distribution. Okay. So we're hand waving a lot of the details for now, because as you know, I dropped the constants, I combine the powers and everything. And I'm telling you almost at this point that if we can arrive at some kind of density looking like a beta density over there, we can recognize the A, we can recognize the B, and then we're almost done over here to recognize that the posterior distribution is another beta distribution. Okay, kind of makes sense? Yeah. So you're going to see that we're going to call this conjugate prior, because we start with a prior, which is beta, and then we end with another prior, with another beta as the posterior. Okay, so this is super useful, as you can see, because, well, if I know this is the beta, I know the parameters, the updated parameters. This is on my posterior parameters, shape, and the two shape parameters. I know those two values, so I know exactly what the distribution is. Okay, I can summarize it. We did some exercise last time, understanding about the beta distribution. Remember the 9 different curves I showed you before? But we can curve this as well if we want. And then what that means is that we know exactly how the posterior of this P going to behave. Okay? So knowing what we call the closed solution of this beta posterior distribution helps us know exactly what the posterior distribution is. And later on, when we get to work with more complicated models, then you will see that sometimes, or oftentimes, we don't know exactly what the posterior distribution is. Because, well, here we use a beta, so everything turns out to be another beta. But if we use a different prior distribution, like normal, for example, okay, if we have a normal prior for P, we still have the binomial likelihood for P. And then everything, if you imagine, might not work out as nicely as what we have over here. So that's why we introduced the conjugate prior, because mathematically they work out pretty well. But they can be a little bit too simplified if we only focus on the simple or easier ones to work with, because a lot of times for priors, we want to use the ones that make most sense for us. Okay. So that's the first version. Like I said, I'm trying to show you that, well, if I don't worry too much about the normalizing constant in the denominator when I'm working with the base rule and just throw everything into the proportionality, I'm able to arrive, okay, let me show you the last slide, okay? I'm able to arrive at this beta posterior distribution. So that's the first version, like I said, and that will be usually the stuff that we're going to work with. And before we go to some kind of understanding of the model itself, I want to show you or ask you to try to do another one, which will be a little bit more involved, but this can help us to make sure that we do arrive at that beta posterior distribution. Okay. So what I'm going to set up here for you is we're going to have our P. Let me try to do this a little bit. Yeah. All right, so we're gonna have our P, that's the prior. So the prior gonna follows, I'm just now gonna use a generic AB over here. Okay, so this is a generic results, and we can do a little bit more exercise over here. So what that means is the prior is 1 over the beta function AB. And we have p to the power of a minus 1 and 1 minus p to the power of b minus 1. Okay, okay, yeah. And then we know that the data, given the parameter, follows a binomial n and p. Okay. So we know that the likelihood function is n choose y, p to the power of y, and then 1 minus p to the power of n minus y. Okay, so posterior derivation, we're working with p given y, right? And notice here that I'm going to use the equation instead of equality instead of that proportional sign. So I'm going to have to keep my p and then my LP. Okay. And then in the denominator, if you remember, for the Bayes rule, we are actually integrating out. So I'm going to use a different, just use p tilde to differentiate it from that p so we don't get confused. And then we're integrating out over p. So my question, or a quick exercise, maybe not so quick, you probably need to think about it a little bit, is try to keep this denominator in place, okay? And try to do the derivation one more time. Earlier, we didn't even work with the denominator because I told you it's gonna be the margin of y. I threw it away into the proportionality, okay? But what I want to say is, even if we keep there, we will still be arriving at the same posterior distribution that we talked about before. So the exercise over here is that please keep expressing this equation for now. And you have your pi p, okay, generically about a and b. You have your LP over here. So you can write out the numerator. You can also write out the denominator using p tilde as the notation, but don't forget the integration over here. But once you get to that step, you might be able to cancel some terms. And then try to work out the denominator a little bit. It is integration, might not be as straightforward, but we know the final answer, right? We know the final should be another beta. So we know the goal to work towards with. And I'll write it out. Okay, actually, I'm just gonna write out. I think the final posterior gonna be another beta, as we know. Generically, it's gonna be a plus 1 and b plus n minus y. Earlier, we did that with particular numbers of a and b and y, okay? But this will be the generic result. Okay? So this is the goal. I'm asking you to give it a try to see how we can arrive at this beta posterior with all of the constants in place. So we can feel comfortable that we are able to throw them away if we are only focusing on deriving the posterior. So this is gonna take a little bit, and I think, so let me pause. All right, so on the screen, I put the first step, and maybe we can take a quick check so we're on the same page, and then you can continue working on it. On the top, I simply just plug in the expression for pi p, right? And then my LP in terms of p. And then in the denominator, remember, I keep the integration because we're not working with the proportional version, we're working with the equality version of this Bayes rule. And what's interesting over here is that because even though we're using p tilde just to differentiate from p, but we still get the same constants. Okay, we still get the 1 over the beta function ab and the and choose y choose function. So with that in mind, you can see that because the integration at the bottom is about p tilde, okay, so it's only about p. Anything else is a constant. So we can actually pretty straightforwardly cancel out those terms for now. Okay? So once again, the denominator is the integration about p tilde. So everything not about p tilde is a constant. Okay? Of course, if you want to write it even more clearly, you can bring out the constants outside of the integral sign, which is fine as well. But at the end of the day, you'll be able to cancel them out. Okay? So that's my first hint for you. So you won't be able to, you don't need to work with these two constants. So now you can see that on the top, you have p to some powers, right? We combine the terms, 1 minus p to the some powers. And then in denominator, you also have, but then everything is in terms of p tilde, and we still have to do the integration. Okay, so that's my first hint. I'm gonna pause here and you can work on it a little bit more and we're gonna look at it together again.
Clarify what the tilde means.
Yeah, so we added tilde over here, mostly because if I keep, so it's this, so we are still trying to integrate out P, okay?
Yeah.
If we keep P in the top and in the bottom, it's just a little bit confusing. People might just want to cancel them out, but
So it
they're,
just represents integration.
yeah. So that's why in the denominator, we use P tilde throughout. Yeah, and you can use other notation. I guess for me, I chose tilde mostly because we're working with the powers about P as well. So I don't want to add like a prime or anything. But that's just a notation preference.
That makes sense.
Yeah. All right, so I did a little bit more work over here, and I'm sure many of you did that already because once we cancel those two constants, we are able to combine the powers for P and 1 minus P in the numerator, and then for P tilde, we actually get exactly the same powers as before. And I should say right now in the top and in the bottom. But the trick, or I guess the challenge over here is that in the bottom, we're working with a integration. And how can we do that integration eventually so we can recognize that this is the correct posterior distribution? So any thoughts about how to deal with that denominator? We're trying to integrate out this P tilde. We have the functional form. P tilde raised to some power, 1 minus P tilde raised to some other power. And then we're trying to integrate that out with P. So what kind of technique we can use over here to get that denominator? Any thoughts? Yeah,
Well, I
Sarah.
have a question.
Yeah,
Are
yeah.
we, like, assuming we don't, like, for the prior,
Mhm.
we know it comes in that form.
Mhm.
So if we know that posterior is going to have, like, those data,
Exactly.
like, you would, by, like, inspection, I guess.
Yeah.
The integral should be equal to the beta, like, the beta function.
With the
denominator.
new terms, right?
Yeah,
Yeah.
with the new one.
Yeah, no, that's a great, okay, so let me restate what Sarah was saying. So, okay, we know the answer eventually. We know that's gonna be a beta with A plus Y and B plus M minus Y. So those will be our new A and B over here. Okay, so we know that if eventually it is indeed a beta posterior, then we should have a constant that we can derive in our derivation. Okay, and that constant in particular, let me use a different color over here. That constant, because of the A plus Y and B plus M minus Y term, whatever that constant should be, the beta function A plus Y, and then B plus M minus Y. We don't know how to get that yet, but if indeed what we did before was correct, that we should be arriving this beta posterior distribution, then in addition to this term, because remember this is our A plus Y, right? This is our B plus M minus Y. So we have this part already. We need the other part. And the other part, as we will see, is actually what this denominator can be integrated to. Make sense? Kind of, at least guessing what we're working towards to. Okay, we're working with this tilde, P tilde A plus Y minus 1, and 1 minus P tilde B plus M minus 1 minus Y, minus Y minus 1, and then we're gonna get to that point. So my next hint for you is that beta, or I should say the beta distribution, okay, is a well-defined density function. What that means is that if you just integrate out P, if you have your beta as the prior, you will integrate to 1. So for a well-defined density function, normal is another example. Okay, we always like to say that the area under the curve is 1. Okay, so for beta, that is true as well. So my next hint for you is, regardless of what A and B you're working with, this is a norm result. So think about how that can help you to derive this to be eventually this. I'm going to pause here. I know it's a lot of information to take in. I'm going to pause here and then let you work through it a little bit more. All right, so what we mean by that hint, like I said, because beta is a well-defined density function. So if you just integrate out P itself with this PDF, it's gonna integrate to 1. So what that means is, if we look at the denominator a little bit more, okay, and we know like our goal is to recognize that it's going to be that beta posterior. So we know that this is our new A, right? And this is our new B. Okay? So if I try to put the denominator into the hint format, what that means is that if I integrate out this particular beta, A plus Y and B plus M minus Y, where I'm going to have this constant 1 over beta AB with my new A and my new B, and I multiply that with P tilde to the power of A plus Y minus 1, and then 1 minus P tilde to the power of B plus M minus Y minus 1, and dP tilde, that should integrate to 1. Okay, so let me say that again. The hint itself is saying that regardless of your AB values, the PDF of beta going to integrate to 1. Okay, and what we're trying to use this hint for is by looking at the denominator over here. And in particular, I can recognize my new A and new B. Okay, and because of that, I can put, so I'm not using this term yet. I'm just saying that the hint itself in the context of what we're dealing with right now is exactly this. Okay, I put my integration because I know the beta density function integrates to 1. So for this beta, A plus Y as the new A, and B plus M minus Y as the new B. And then I also need to have this constant 1 over this new B, A plus Y, and M plus B plus M minus Y. This whole thing integrates to 1. So with that, the last step that we need to do, as you can see over here, is that we know this whole thing integrates to 1, but the denominator only gives us everything that is not about the constant. Okay? So if I move out this constant outside, what that means is that the integral itself gonna be 1 over that constant. So what I mean by that is that whole thing is gonna be B A plus Y and B plus M minus Y. Let me say that again. Okay. So we know this is the hint itself. Okay, this is specifically to this context, and then this constant is not in the denominator. Okay, but the denominator is only integrating everything without the constant, and we know that with the constant, the integration integrates to 1. So if without the constant, the integral going to integrate to 1 over the constant. So definitely a lot of information, like I said. So I will say that one more time. The hint is that the beta density integrates to 1, no matter what your A and B is. For us, we're trying to use that hint to recognize what the denominator is like. The denominator right now does not have any constant, right? It just has P tilde to some power minus 1, and 1 minus P tilde to some other power minus 1. And we're integrating that P tilde altogether. Okay? So the hint, if we want to use the hint in this particular concept means that if we're integrating P tilde to the A plus Y minus 1, 1 minus P tilde to the power of B plus M minus 1 minus 1, if I just add that constant, that beta constant for this particular beta distribution, it's going to integrate to 1. So all to say is that with this constant, because of the well-definedness of the beta density function, with this constant, it's going to integrate to 1. And all we need to know, or all we need to do is we're integrating it without the constant. So we just need to put the constant out. So with the constant, we integrate everything into 1. And if we don't have the constant, it's just going to integrate everything to 1 over that constant.
We're just multiplying and dividing by the constant, right?
Yes, exactly. So here, yeah, thanks. So here we have the constant is 1 over this beta function. And because it's in the denominator, so eventually this whole denominator just becomes the beta function of A plus Y and B plus M minus Y. So what that means, so yeah, so I just need to, I guess, be super helpful. I'm just talking about the denominator now, which is the beta constant, which is the beta function. And then because in the denominator, so in the end, you're just going to get 1 over that beta function. And because of that, you're able to recognize that is beta this particular form. Okay. Okay. So we'll take some time to digest, and this is probably the most intensive derivation we're going to do in class. I think I will do another one when we get to next chapter. And this kind of derivation really only happens when you work with simple models like this, because you will be able to recognize what the posterior distribution is. And you will see that in a lot of cases, you won't be able to have it because models are more complicated, or the prior might not be what we call conjugate, because you might not be able to recognize what the posterior distribution is. And when that happens, we're going to rely on computation. So the derivation wouldn't matter as much in those cases. But the key message I want you to take away over here is that earlier, so let me just bring this back. And oops, sorry. And let me try to see. How can I? Oh, okay, yeah. So what I was trying to do, sorry about that, is to show you that earlier in our derivation, yeah, in this version of the derivation, we didn't even worry about the constants and everything, right? And we actually arrive at this beta. And all of the exercise that we did just now is trying to convince you that even if we keep the constants, we'll arrive at the same beta posterior. So the process of not worrying too much about those beta function, like all of those, not worrying too much about them, will still be fine. Okay, you will arrive at what we claim to be the beta posterior. And like I said, later on, we won't be doing as much derivation anymore. And in particular, we're going to mostly use this proportional sign instead of using inequality, because we can see that they do arrive at the same result. So what we did just now, first of all, is the exercise to get you see how posterior derivation can be carried out for a continuous version of the base rule. And secondly, trying to convince you that even if we don't worry about the constants, we will still arrive at what we supposed to arrive. So maybe in the future, we don't need to worry about those constants anymore. Okay. And this whole derivation itself, I think I also left as a homework exercise for homework 2. So you will get the chance to work through the details one more time, and then make sure that you get all of the little things here and there. Okay. So to summarize a little bit, from beta prior to beta posterior, we start with the beta AB prior. We have a sampling or likelihood that we're working with, which is a binomial. And eventually we'll arrive at this posterior distribution. Generically is A plus Y and B plus N minus Y. Okay. So we call them conjugate priors because you start with the beta prior and you arrive at a beta posterior. They're different betas, but at the end of the day, they are from the same distribution family. And when that happens, we call them conjugate priors. And I have a little table over here just to show you the general results, okay? And you can think about this updates in this way as well. If my prior has A and B, okay? And we're gonna talk about what we mean by success and failures in a second for A and B. But if you look at the middle column, the middle row over here, remember Y is the number of successes, right? So N minus Y will be the number of failures in the data, right? So if we think about A as the prior number of successes and B as the prior number of failures, you will see that this posterior update for this beta prior arrive at this posterior beta as A plus Y as the success and B plus N minus Y as the failure. Okay. So I know it might not be as intuitive as thinking about A and B as the number of success and number of failures, but it's pretty straightforward to think about that in terms of the data model, right? Because we know Y is the number of successes and N minus 1 is the number of failures for a binomial density function. And we can do that similarly for the prior, for the beta as well. And if we understand in that way, you can see that the posterior is exactly a combination of the prior and the data. Okay. So I know earlier we talked about this beta select function. Remember, to get the quantiles, you want to pick a particular beta prior if you have 2 quantiles of interest, and you can use the beta select function. Now I'm introducing another way to think about how you can solicitate prior. So A represent the prior number of successes you think you might have, and B represent the prior number of failures you might have. So for example, if I think my success to failure rate is 1 to 4, let's just say, I can choose A to be 1 and B to be 4. Okay? And a natural question you might be wondering is, oh, okay, I can also choose A to be 10 and B to be 40. That will also be 1 to 4. Okay? So I think in one homework exercise, I also asked you to experiment that a little bit. And the general story over here is that if you think about A plus B, A plus Y, and B plus M minus Y over here, you can see that the posterior is a combination, actually in this case, the sum of the prior and the data likelihood, right? So the data is fixed. It is Y and M minus 1, like nothing can change because we gave out 20 survey and then we got 12 yeses. But A and B, if you choose 1 and 4 versus 10 versus 240, I think the prior, I should say the prior influence of what 10 versus 40 are going to be much bigger. So that's what we mean. At the end of the day, the posterior is always a combination of the data and the prior. Okay. If you have a very strong prior, or you have strongly believed certain things, you might want to give A and B large values. Because when they turn out into the posterior parameters over here, they will have a higher weight than a smaller A and smaller B. Okay. Okay. So that's the general idea. Okay, so keep that in mind. Like I said, we have some exercise over there for you to practice as well. And of course, in R, everything is pretty straightforward because once again, we know the posterior distribution is a beta. Okay, so I just write out my A and B. That's my prior in the first place when I was using the beta select function. Okay, and then my data is 12 and 8. So this is representing Y, and this is representing M minus Y. Okay, so I'm getting my success and failure in the data, my prior success and prior failure in the prior distribution. So in the end, it's pretty straightforward because from the table as before, we're just adding them up to get the posterior shape parameters. Okay? The sum of A and Y is the posterior, the first parameter for the posterior, and the sum of B and M minus 1, that gives you the second parameter for the posterior. And then lastly, before we start working on the lab, is I want to show you a density or two density plot together, overlay one over the other. Is the prior that we used earlier. And then now is the posterior once we have our data Y to be 12 and N to be 20. We like to do this just to contrast, you know. Before getting the data, we have a prior belief. And then in this case, we have a beta prior. And then now the data comes along and then we update using the beta posterior method that we talked about. We get to this posterior in particular. Okay. So I have two questions for you, and then we're going to move on to do the lab today. Exercise 1 is compare the prior mean, which I give it to you is 0.544. That's just a analytic solution from the prior that we have, okay? And the posterior mean. Compare them and discuss how they, I guess, differ from each other. And I will also say that because Y equals to 12 and N equals to 20, so the sample mean is 0.6. Okay? So the story is, once again, how can we use this result to reason through that the posterior is a combination of the prior and the data. The second one is, if you remember, we not only say that we can update the prior to the posterior, but we can also sharpen our belief about the parameter through this Bayesian inference. So my second exercise is compare the spreads or the variability of the two curves and think about what we mean by we can have our sharpened belief once we can do this update. So with that in mind, I will pause. All right, anyone has any thoughts about either one of this or both? If you feel like sharing your thoughts. First one is about the mean. The second one is about the spread, or you can think about it as the variance. So we're looking at the two main summary statistics, the mean and the variance of the prior, compared that to the posterior. Anyone? Yeah, Kara.
Well, for the spread, the posterior spread is less, it's more precise, which is what we want. So, you know, getting more data from the prior is the more precise.
Yeah, sounds good. So this is about exercise 2 over here. So we can really just compare the spread on the x-axis. Okay, so you can see that roughly the prior, as we know, is anything from 0 to 1, right? Even though we have a peak, I guess, a little bit more than 0.5, but nevertheless, you can see this curve that it covers the entire 0 to 1 span. And then the posterior is much more concentrated. Okay, it's much more concentrated. I think the mean, so we're going to talk about exercise 1 in a second as well, is similar to the prior to some sense, but it's definitely, as we will see soon, that it's a combination of the prior mean and the data mean. But more importantly, we see that the spread is much smaller, okay? Meaning that we have less uncertainty about the parameter because of the inference that we're able to do. And by the way, both of them are beta density. So both area under the curve is 1. Okay? So that's why if you have a wider spread in the prior, you're gonna have a shorter, right? The whole density itself. And then if we have a shorter spread for the posterior, it's going to be more peaked. And then anyway, so area under the curve for both of them is 1. So this is what we see. And anyone wants to talk about exercise 1 quickly? In terms of the mean, we have the prior mean, we have the posterior mean, and the sample mean. So what do we see over here? Compare the 3 values. Yes, Sarah?
So we see that the sample mean is 0.6. And previously we got some prior that had a mean of 0.544. And once we knew about like the data, we see that the posterior mean gets shifted / driven by the data towards that sample mean. So it's still going to be less.
Yeah, great. So just by looking at the 3 numbers, we can see that, well, the posterior mean is in the middle, right? Between the prior mean and the sample mean. And with this is one justification, or I guess illustration of what we mean by the posterior is a combination of the prior and the data. And you also see in the homework exercise that the posterior mean is actually going to be a weighted average between the prior mean and the sample mean. The weights themselves, just a spoiler if you call that way, it's going to go back to this table itself. So if you remember, I was saying B and A, or A and B, I should say, we think about them as the prior success and prior failures, okay? And then the data is fixed, y and n minus 1, and we can see that the posterior, the two shape parameters going to be exactly the sum of the 2, okay? So you will see in that exercise of, well, if I fix my size, I should say fix my data, and remember I gave the example of like 1 versus 4 or 10 versus 40. Even though both of them, I mean, in terms of A and B, let me say this way, even though both of them kind of saying that failures in the prior are 4 times as likely as the success, but they carry different amount of information. Okay? And you will see that once you start to do that exercise, to see what we mean by the posterior mean is a weighted average of the prior mean and the sample mean, and then how large A and B are. The larger they are, the more information you have in the prior, and then the posterior are going to be more heavily influenced by the prior. But if you choose smaller A and B, even if their ratio stays the same, just like 1/4 compared to 10/40, you will see that the inference is going to be driven much more by the data than the prior. Okay? So we talked about those general ideas many times by now, and right now with these simple models, we're trying to you see in action numerically as well as mathematically to see why that is the case. And then as we move on, like I said, with more sophisticated models, we might not have the luxury of working through the math as nice as we can do right now, but the general story still stays the same. Okay, that is the prior and the data together influence the posterior. Okay, and so in this beta case, it's going to be a weighted average if we think about the mean once you do the exercise. The second one is about this exercise too over here, that the posterior update that we're dealing with can always help us sharpen our belief. And that sharpen is in terms of how much uncertainty you have in the prior compared to the posterior. Okay? And lastly, because the posterior is a combination of the data and the prior, if you have very strong prior, the posterior are going to be more heavily influenced by it. If you do not have a very strong prior, then the data are going to drive more of the inference. So there are always these 2 forces pulling each other. And with that, I just want to end this part. So on Friday, we're going to talk about this Bayesian inference with continuous priors. So we're going to talk about hypothesis test, credible intervals, and prediction. And then that will wrap up this whole section itself. And